Good morning, everyone, and thank you very much to the organisers for the invitation to come here. So I'm going to talk about some relatively recent work that I was doing when I was working in Italy in Trieste. So this is joint work with Francesca Arici, who is at CISA. Morning. And Giovanni Landi, University of Trieste. So Francesca's here, so Gianni will come later, I think. Okay. So, let's see. So let's start just by introducing some of the words in the title. Good morning, everyone. Are you awake? So, what do we have? Well, projective spaces, these are easy. These are things that everybody knows. The easiest way to get them is to, well, for me, is to think of them as being the quotient of an odd-dimensional sphere by an action of U1. The action I'll give you in a second if you don't know it, but I think everybody pretty much knows this. And sitting inside this group U1, you get a copy of the cyclic group ZR, sitting as rth roots of unity. This will all be explained in much more detail shortly. If you take the quotient of the odd-dimensional sphere by this circle, this cyclic group, then you'll get a length space. And these give me principal bundles, U1 principal bundles. Well, sorry, the first one is a U1 principal bundle, so that no, that's not true. The first one is a ZR principal bundle of the sphere over the length space, and then the second one is a U1 principal bundle with the length space over the projective space, and I'll denote this bundle map by pi. And what you get from this is an exact sequence in K-theory. I'm not claiming this is obvious how you get this yet, but you get a sequence from the odd K-theory of the length space into the even K-theory of the projective space, back into itself, and then into the even K-theory of the length space. What are these maps? Well, this delta is a connected homomorphism that you usually find in exact sequences in K-theory. This alpha is multiplication by the so-called Euler class. So this is, if I take the canonical bundle and raise it to the rth tensor power, that's this guy, and then its Euler class is 1 minus the class of that line bundle. So that's this map is multiplication by this class, this line bundle. And then pi star is just pullback. So if I have the length space sitting over the projective space, then this map here is just pullback of line bundles from the projective space to the total space. And that's an exact sequence, and that's fun because if I know the K-theory of the projective space, which I happen to know, then this immediately tells me the K-theory of the length spaces. So I get the K1 of the length space as the kernel of this map because of exactness. And I get K0 as the co-kernel of this map, again, because of exactness. So the proof of this I'm not going to give you right now, because this will come later in a more general setting. But the proof comes from constructing, well, so I start with an exact sequence in relative K-theory. And this gives me a 6-term exact sequence so I start with an exact sequence of relative topological spaces. This gives me a 6-term exact sequence in relative topological K-theory, and what I do is I make some homotopy arguments to reduce to this sequence. So the key word here is homotopy. So what I do is I start with a sequence that I know is exact, and then I homotopy it into this one. So that's the strategy of the proof. And you'll see that coming up a little bit later. So why am I interested in length spaces, and in particular non-commutative length spaces? So this will come later. This is I've given you the Gysin sequence and the words length spaces, but we want to insert the word quantum in there, but why am I interested in that? So just a brief slide on motivation, and then this will come back at the end. So the strategy here is that you're interested in, well, I'm interested in gauge theories on, first of all, classical length spaces. Later we'll make these quantum. So one example is if I take the length space L1R, so this is where n equals 1, so this is a three-dimensional manifold, smooth manifold in my cases. And I have the Chern-Simons action, which is given by this formula here. So I take the curvature of the connection of a connection one form. So A here is a connection U1, a UN connection one form, a trivial bundle over my length space. I form its curvature. I wedge it with the connection one form. I can cube it. I can integrate, take the trace and integrate over the manifold. This gives me an action on the space of connection one forms over the length space. I have another option, which is Yang-Mills theory on S2. So this is, the action here is perhaps more familiar, and this is given by this formula. So here is the star is this, the Hodge operator. And as I mentioned on the previous slide, I have a principal bundle here. So in this case, it's L1R sitting over S2, so CP1 being S2. And these two theories are related very intimately. So every critical point of the Chern-Simons action is related to the Yang-Mills action on S2. So I have the length space sitting over S2. And every critical point upstairs is given by a pullback of critical point downstairs. Oh, well, a direct sum of these. So I have direct sum of, so constant curvature connections downstairs. These are the minima of this action. These are in turn direct sums of monopole connections on S2. And this is, I mean, if you know anything about K-theory, then surely you know the K-theory of S2. That's the one thing you're in, the first example of a non-trivial K-theory that you study, I think. So the K-theory on S2 is generated by the trivial bundle and by the bot projection. So you can take tensor powers of the bot projection, and all of these constant curvature connections are given by direct sums of these things. I'm not claiming that's obvious, it's just a fact. And if I pull them back to the length space, I get the critical points of the Chern-Simons action. So the question is, how does this work in non-commutative geometry? We're interested in studying Chern-Simons actions for non-commutative three manifolds, in particular non-commutative length spaces. So the question is really, or the motivation, the beginning is, okay, we know very well what happens with Yang-Mills on quantum two spheres. This has been well studied. There are too many names to even mention here. But does the study of this relationship between Chern-Simons upstairs and Yang-Mills downstairs tell us something about, so we know that the Yang-Mills downstairs, can we learn something about the Chern-Simons upstairs? I'm not going to tell you the answer to that because I don't know, but the idea is that's where we're going with this, and the idea here is to understand how the topology downstairs, so the monopole connections and so on, the Yang-Mills theory, via K-theory, how is that related to the K-theory upstairs? So I mentioned Oliver Pfanter here. So he wrote some nice papers on trying to understand Chern-Simons for non-commutative three manifolds, but there are some problems, and one needs a fresh approach, and so we hope that this gives some insight. So let's introduce the word quantum into all of this. So quantum means nothing to do with quantum physics. This is quantization of algebras. So first of all, let's introduce what we mean by a non-commutative odd-dimensional sphere. So I mean this in the sense of Vaksman-Soibelman. These are the odd-dimensional quantum spheres. So Q here is going to be a deformation parameter between 0 and 1, or it could be equal to 0. So in the real interval 0, 1, including 0. So this is generated by a bunch of coordinate functions, so zi and zi star. There's n plus 1 of the zi's, and then there's n plus 1 conjugates. There's a bunch of relations here, which I won't tell you, you don't need to know them, but the deformation parameter q is telling you how the zi and the zj commute. So this is for I less than j. There are a bunch of other relations. You don't need to know them. More importantly, you have this sphere relation, which tells you that you're not on R to the 2n plus 2, but you're on 2n plus 1 dimensional sphere. So this is the algebra generated by these, the unit algebra generated by these guys, subject to some deformed commutation relations, and the sphere relation. And of course, as q goes to 1, you recover a commutative algebra. This is the algebra of functions on the classical two-dimensional sphere. Now, this stuff carries a u1 action, so I can just multiply the coordinates by some value lambda in u1. And then I can take the algebra of invariant functions under that algebra. And this is what I call the algebra of functions on CPN-Q, so the quantum projective space. So this is by definition the coordinate algebra of functions on the quantum projective space. It's easy to see that this is generated by polynomials of this form. And this gives me a quantum version of the U1 bundle that you already know. So what I think of as the quantum 2n plus 1 sphere sitting over the projective space CPN-Q. And this is a principal bundle in a certain sense, which I won't define, but really what it means is that there's a certain condition which says that this U1 action is free in some non-commutative sense. So I have coordinate algebras, quantum sphere sitting over quantum projective space somewhere here. And I define C of this guy and C of this guy to be the enveloping C-star algebras. So these are what I think of as the continuous functions on these spaces. So I start with coordinate algebras, and then I take the C-star envelopes of those things, and these gives me what I think of as the continuous functions. And the K-theory of this has been worked out in various different ways. I'm going to mention some of these other ways, but the first one that I want to mention is by a paper of Francesca and Giovanni Landi. This was a few years ago. And this says the following, that I can find projections of a certain rank dn, or a certain dimension dn, with values in the coordinate algebra of CPN. So we're looking at the K-theory of the projective spaces here. There's n plus 1 of them. That's little n plus 1 of them. And I take their classes in K-theory, and this generates the K-theory of the K0 of the C-star algebra. So this is the point I want to emphasize here, is that I'm interested in the K-theory of the C-star algebra, but I can find generators whose entries live in the coordinate algebra, which makes life a lot easier because we're interested in computing. So I mentioned these gauge theoretic actions, this Chern-Simons action and the Yang-Mills action. So really that means doing index computations. And if I'm living in the coordinate algebra, then my index computations are very, very easy comparatively. So this is kind of interesting because when Q is away from 1, I've really quantized the C-star algebra. I've deformed it into something different. And so it's this usual picture of having a continuous field of C-star algebras, so the K-theory stays the same. But what's useful is that I can still find algebraic generators of the K-theory. And if you look at the modules, so let's say right modules associated to these projections, it turns out modules over the algebra, the coordinate algebra, then it turns out these are actually bimodules. So a priori these are right modules, but you can actually check just by writing down what these things are, that they're actually left modules as well. People are sometimes confused by this. If you know the construction, it's easy, but if you don't, then maybe I should say what it is. It's simply that each Ln is isomorphic to the coordinate algebra of the length space, and then there's a cotensor product over some representation of U1. And so left and right multiplication by this guy gives you a bimodule action. And in particular, these guys have a certain property. They say that if I take two of these modules, Ln, and I tensor over the base algebra, then these numbers, n and m, they add. And then that means that if I take a higher tensor power, so Ln raised to the power m, over this coordinate algebra, then I have this property that I simply multiply this charge n by the tensor power m.
Sorry, how are the big N and R related here? Are they related?
A priori, no. But certainly, I mean, there are various cases where I mean, there are various isomorphisms between. I mean, usually you take them to be co-prime or something like this or whatever, but I don't need to add any relations.
So are the LNs
Morita
Morita equivalences?
equivalences, yes. Yes. In fact, we have Francesca in the audience here, who I'll say a little bit more about that later. But that's actually this always happens when I give this talk, and then people make smart observations that make the whole thing a little bit easier. I will come to all of these things, because all of the experts here are going to immediately come up with probably 5 or 6 different alternative methods of proving this. I will hopefully say a little bit about those later. So with these modules, with these bimodules, you compare them with K-homology. So this is again something that Francesca and Giovanni did. And you find that the Chern number, so the C0, so pairing with the 0th class in the trivial class in K-homology, this gives you the answer 1. So the C0 is thought of as the rank of the bundle. So this is telling you that really you have an analog of a line bundle. And then the first Chern class, it comes out to be minus n. So you can think of this number n as some kind of non-commutative analog of a winding number. So I think of Ln as being the space of sections, as we usually do in non-commutative topology, as the space of sections of some line bundle over this quantum space with a winding number minus n. Then we went a little bit further and we showed that if I take the analog of the Chern class, of the Euler class of this space, so I take the canonical bundle, what I think of as the canonical bundle, the one with winding number 1, and I take its Euler class, which I define to be 1 minus the class of this bundle, or this module, you find that actually the K-theory of the projective space is generated by this class, modulo setting its n plus first power to be 0. And this is isomorphic to a copy of the integers to the power n plus 1. So actually, the whole, just as in the classical case, I should say, the entire K-theory is generated by this Euler class. So that's the K-theory of the projective space. I'm going to need that later. How about lens spaces? I need the quantum version of lens spaces. So what are we going to do? So we worked a little bit and thought quite hard about how we wanted to make this definition. Immediately, some of you are going to say, well, there's a different definition, and it's going to be the same. So if R is bigger than 2, I mean, if R is 1, then this is doing nothing. So we're going to take R to be greater than or equal to 2. We define the algebra, the coordinate algebra of the quantum lens space to be the direct sum of all of those, all of these modules of sections whose charge is divisible by R. And this is what we call the coordinate functions on the quantum lens space, L, N, R, Q. And then we take the continuous functions on the space to be the enveloping C-star algebra of that. So this was our definition, the direct sum of all bundles whose charge is divisible by R. And you might say, well, but in the beginning you defined this to be the classical situation, you defined this to be the quotient of an action of the cyclic group ZR. And that's exactly what happens here as well. This guy is a star algebra. It's the subset of all elements in the coordinate algebra of the odd-dimensional quantum sphere, which is invariant under the z action given by multiplying by rth roots of unity. So you have algebra inclusions. So you have the coordinate algebra of the projective space sitting inside the lens space, sitting inside the quantum sphere. And we had that on the very first slide. That was this picture here. But of course, when you take algebras, you reverse all of the inclusions. And so we have this series of inclusions here. We've already seen that CPN sitting inside S2n plus 1, that this is already a principal bundle, a U1 principal bundle. Now we're interested in the lens space, the projective space sitting inside the lens space, coordinate algebra-wise. This is also a quantum principal bundle, so there's some certain freeness action going on here. And this also has a structure group U1, which actually we write as U1 tilde because CPN sitting in, the sphere sitting over the quantum projective space, that's a U1 bundle. This is a ZR bundle. So here, to get the structure group, I have to take the quotient of U1 by ZR, which is again a copy of U1, but you have to keep track of these things. So this is what I call U1 tilde. So there's an action of U1 tilde acting on the coordinate algebra of the lens space. And that's a quantum principal bundle. So there's a certain freeness condition here, or if you prefer, Hopf-Galois extension. That's all it is. So we've got the quantum picture that we had in the classical case. So we'd like to construct some kind of sequence in K-theory for these guys. And so for each Ln, so these are modules over the projective space, or the algebra of the projective space. We can define its pullback just by making a change of coefficients. That's the usual picture. So I tensor with the algebra of the lens space over the base space. This is what I call Ln tilde. And this induces the usual map in K-theory. So it sends, so this is, classically I think of this as a pullback of bundles once again, but in the language of algebras, this is a push-forward map in K-theory. So it sends the K-theory of the projective space to the K-theory of the lens space. And I want to make an important observation here, is that we already noticed from Francesca and Giovanni's theorem that everything here is algebraically generated. So the K-theory on this side can be written in terms of coordinate algebras. I don't know that that's true at this level, at the lens space. So it gives me a map. It doesn't say anything about whether this is surjective or anything a priori. So I want to stress that we would like to have an algebraic situation over here as well, but we don't know that that's true. So we can start with algebraic generators, but we don't know what happens over here. So the map is just given by this pullback map or push-forward map, depending on what you prefer. And then let's try to get a bit of information about the K-theory of the lens space. So downstairs on the projective space, so here, the module Ln is free if and only if n equals 0. And it's important to note here that this is L0. That's the only time when you have a trivial bundle. But then, this is where the project really got off the ground, when Giovanni made a very nice observation, I think, is that if I take the pullback of the rth tensor power of the canonical bundle, so I take L minus r and I pull it back via this construction, so I change the coefficients, then I have L minus r tensored over the base with the functions on the lens space. But remember that the functions on the lens space were just the direct sum of all the tensor powers. They were the direct sum of the modules whose charge was divisible by r. So if I'm tensoring like this, and you remember the tensoring rules, this says that I shift the charge by minus r. So that does nothing, because everything is divisible by r. So I really do nothing. And so the pullback of L minus r is isomorphic to the pullback of L0. So upstairs, the pullback is free. It's a free module. So this tells me, for example, that if I take the canonical bundle, rth tensor power, pull it back, I get the free module, the trivial module. So this tells me that the pullback of the canonical bundle is torsion, because its rth tensor power is trivial. So downstairs there's no torsion, upstairs there's torsion. Already starting to see some structure. So that's one map. I have this, we call it pullback because we're really thinking of the topology here, we're thinking of bundles. But if you're an honest K-theorist, then I guess you prefer push forward in the algebra setting. So there's another map here which goes from K0 to K0. And this is again multiplication by the analogue of this Euler class. So this is 1 minus the bundle with charge minus R. So we've got two maps. And so this is telling us now we can maybe try to start to put this into a sequence. So here's the map alpha, which is multiplication by the Euler class, K0 to K0. I've got a pullback map, or push forward map, from the K-theory downstairs to the K-theory upstairs. I can put a 0 here, I can map everything to 0, that's not a problem. So we're looking for a sequence of this type, it's just that this arrow is missing at the moment. K1 of the lens space into K0 of the projective space. Classically, that was the connecting homomorphism. How on earth are we going to get that? Because you remember I told you that you had to start with a sequence that you knew was exact, involving a connecting homomorphism, and then you had to homotopy it. But we're starting a priori with the quantum spaces already. We don't know, we haven't started with an exact sequence, so we don't have a connecting homomorphism. So we'd like to build it. The experts in the room will already know how to do this. We're going to go into KK theory because connecting homomorphisms are index maps. For those of us who like this kind of language. So let me shorten the notation a little bit. I'll write capital A for the functions on the lens space. So maybe I should write this just to keep the notation in mind. So we're going to work with C-star algebras now. This is the continuous functions on the lens space, and F will be the continuous functions on the base space. So remember, this is a principal U1 bundle. So there's a copy of U1, well, U1 tilde here, acting on this C-star algebra, and the invariants are the functions on the base space F, CPNQ. So F I write for the invariant functions. So here, F is the fixed point algebra of A under this U1 action. And because I've got a compact group, I can write down a conditional expectation Tor, which is just integration of averaging over the group action. And in the usual way, this gives me an inner product with values in the fixed point algebra. So if I start with a pair of elements A, B, and capital A, I can take A star B, average over the group action. This gives me something in F. This is an F valued inner product. That gives me a topology, so I can define the norm of some element. Rather than the C-star topology, I can take the topology given by the norm given by taking the inner product of an algebra with itself, and then I can take the norm in the fixed point algebra. And this gives me a different topology, a priori, which when I take its completion, the completion of A, I'll call that X, and that gives me a right Hilbert module over the base space algebra. And for each integer k, we'll denote by AK the corresponding spectral subspace. So this is a Fourier decomposition. These are the elements of A which have weight k under this U1 action. So in particular, we have, as I've already written here in the algebraic setting, A0 is just a fixed point algebra. And the important observation is that this action has what we call full spectral subspaces, in the sense that if I take the subspace generated by elements of the form AK star A, and then I take the completion, this gives me a copy of F for every k. And from this I can build an important KK cycle. So I let D be an operator from this Hilbert module to itself, to be the infinitesimal generator of this action. And it's quite easy to see what this is. You've seen this before in some form or another. This operator, so it's densely defined on this domain, which I've written it, but it's not so important to understand what's going on. Really what it is just a number operator. So given any element xk in a spectral subspace, it multiplies it by the weight. That's the infinitesimal generator, as you can see by this formula. And that's a densely defined operator. Turns out, due to a theorem of Carey, Nest, and Rennie, that this is actually a self-adjoint operator. It's also regular. And the pair xd, this determines a class which I'm going to call lambda in the KK theory, so the odd KK theory, KK1 of AF. If you don't know anything about KK theory, then all I will tell you, and this is enough for this talk, to know that you should think of elements here, so cycles or classes here. These are AF bimodules equipped with a self-adjoint regular operator. And then I take certain homotopy classes of these things. Well, upon taking the bounded transform of this. But so given one of these things, I can take a bounded version of this D. This gives me a Fredholm module, and then I take certain homotopy equivalence relations. But for this talk, it's important to know that really I have a bimodule, an AF bimodule equipped with this operator. That's what you need to know. So we have this module equipped with a nice operator. Now, once I have this KK cycle, I can construct, well, I can use the Kasparov product. I'm going to use the usual trick of not actually telling you what this product is. No one ever tells you what it is, except in the books. So I'm not going to tell you either. Just to know that I'm going to take K1 of the complex numbers A's with A. So these are CA bimodules. So that means really just write A modules. And this KK1 of AF, so this is where this class lambda lives. And Kasparov tells us that when we have the right factor here and the left factor here agreeing, then we can contract. And there's a nice product there, which we denote using tensor of A. This, I guess, this is all Z2 graded. So the point is that I can contract this A, and I'll land in K of CF. This is here. This is a Z2 graded theory, so the odd times odd goes to even. And it's just a fact that K1 of the complex numbers with A is, so that should be a KK1, that's a mistake, and that should be a KK0. So KK1 of CA is just the odd K theory of A, and KK0 of CF is the even K theory of F. And this allows me to define a map from K1 of A to K0 of F just by taking the product with this element lambda. So those of you who know this stuff backwards can wake up again now. So this gives me a map just by taking the product of this class lambda, going from K1 of A to K0 of F. And I denote it by an index symbol because really what this map is I take something in the K theory of A, I twist it by this class lambda. So I take the element of K1A, I tensor everything with this class lambda, and I take the index of the resulting map. That's why this index I use this index notation. So it's very computable. And I put all this together, and so now I have this map that I was looking for. I'm not saying that I know anything about it, but it really does go from K1 of the lens space into K0 of the projective space. And then I have this map, alpha, I have this map, which I think of as pullback. It gives me a sequence. Our claim that this is an exact sequence. So I'm going to say a few words about how to prove this and what we do with it. So our proof, it's not the only proof, but it's our proof. This uses the mapping cone construction. Again, this will be familiar to a lot of you. So I have the suspension of my C-star algebra A, which is just functions from the interval into A vanishing at the endpoints, going to 0 at the endpoints, into the mapping cone. So I have an inclusion. And if I evaluate at the endpoint, so if I evaluate at the endpoint 1, I'll get a map into the fixed point algebra. This is the definition of the mapping cone, so it tells me that at the endpoint 1, I land in the C-star algebra F. And we know that we can lift, well, okay, so we have to construct this, but this class that we wrote, so this AF bimodule with this infinitesimal generator, which lives in the odd KK theory, you can lift this to the K theory of the KK theory of the mapping cone with the fixed point algebra F. And you do this as follows. So you go from K1 of AF into K0 of MF. So you tensor with L2 functions on the half interval. You take this function which says, well, okay, I differentiate in the first section, the first leg, and I act with D in the second leg. And then I double everything. So this is quite a usual construction to go from K1 to KK1 to KK0. You double the action. So everything is now Z2 graded, so it lives in KK0. And then you have a theorem which I think is quite a deep theorem. Maybe it's because I'm not an expert, but this is very hard work, I think, to show that if I double everything and lift this operator, this does indeed give me a class in KK0 of the mapping cone with F. The reason that this is hard work is because this lift is a priori, well, this is not a self-adjoint lift, and you have to work very hard to fiddle with the domains a little bit to make sure that you get a self-adjoint operator at the end of the day. So what you get is symmetric. You have to fiddle with the stuff a little bit, and this is very nice work, I think. But this was really perfect, because so this is where the story becomes nice, because well, okay, so I'll say a little bit about the history. So we were trying to prove that this sequence was exact. So this is Francesca and Giovanni and I. We had this, I guess we knew that this was an index map. But we had it very concretely, very explicitly, and we were trying to compute that this was an exact sequence by actually taking classes, computing the index, and so on, and showing that really you had an exact sequence. Because we, as I said, with the classical situation, you start with a sequence you know is exact, and you homotopy into the thing you want. We don't have a thing that we know is exact at the moment, so we're kind of left with just brute force to try to show that this is exact. But then I went to Wollongong to visit Adam Rennie, and so that was kind of interesting, because then I went to give a talk to the leading experts in graph C-star algebras and tell them something about graph C-star algebras, which is dangerous because they know more than I do by a long way. And at that point, I had an email from Francesca, and she told me, hey, these things are graph C-star algebras. We know something about those, right? I said, no, I don't. But maybe you should ask the people in Wollongong. So I did. And Adam, he explained to me about this mapping cone construction and how this stuff works. And from that, once we understood that, so from this exact sequence, so the point is we do have a sequence we know is exact. It's this suspension, mapping cone, fixed point algebra. And from that we get a 6-term exact sequence for free, almost, if you read the textbooks. So you have the K theory of the suspension, so K0 into the K0 of the mapping cone into K0 of the fixed point. Then you have a connecting homomorphism into K1 and so on. But yeah, Francesca's observation was that these things are all graph C-star algebras. And what do I mean by that? Just three words on that. Well, 3 sentences on that. If you have okay, I don't even need to write anything. If you have a directed graph, Then to every vertex of the graph, I can associate the generator of an algebra. And between every time I have an edge, I can associate some relations between those generators. So I have generators and relations associated to a graph. I take the C-star completion of that. That gives me a C-star algebra, and then you can more or less deduce everything you want to know about the K-theory and the K-homology just by looking at the graph. And in particular, you know that the K1 of F must vanish. This is all quite involved. I'm not going to say anything about it because there are experts here who are much more knowledgeable than I am. And also you know that K1 of the mapping cone must vanish. This is because the graph has particular properties. So this is not true in general, but if you have a graph with nice properties, then these two K groups have to vanish. So then we said, okay, well, we have a sequence which goes from 0 into K0, into K0 of the mapping cone, into K0 of the fixed points, to K0 of S1, and then we have 0 again here. So that's this sequence here. So really this is the induced map from the mapping cone, from the suspension into the mapping cone, the push forward of the evaluation map, and then a connecting homomorphism, which is this guy. We have an exact sequence. Bingo. Here's the one we started with, the index map, multiplication by the Euler class, and then this, what we think of as a pullback map, push forward if you like. And we would like to relate these two sequences. Brilliant. So this is the bit where talking to people helps. What we can do is we can write down vertical maps. This is just the identity map. To me, that's the K0 of SA is by definition the K1 of A. Again, because F and A are graph C-star algebras with nice graphs, they have nice properties, there's no crazy stuff going on. This is an isomorphism. I won't tell you what it is, but these two things are isomorphic. The K0 of the mapping cone is the same as the K-theory of the fixed points. This square commutes, and this is, again, what I think is, I don't think, no, that should be 2010, sorry. And this you can think of as some kind of non-commutative Atiyah-Patodi-Singer index theorem, which tells you that if I lift the mapping cone and put certain boundary conditions, so this is what I was saying here, is that this lift to the mapping cone is symmetric but not self-adjoint, so you have to work a little bit. And the question is really, what are the boundary conditions I put on the mapping cone? What are the boundary conditions on this operator? So I lift with certain boundary conditions and make sense of what that means, and that's the difficult bit. Then you find that this diagram commutes, so lifting, well, okay. So taking the index of the operator I started with is, up to K-theory, the same thing as lifting and then taking a lifted index. And then you're in good shape, because then you can work a little bit and say, well, K1 of the suspension, that's K2 of A, which by the inverse of the Bott isomorphism is just K0 of A. And then I would really like to have a map here to make this whole diagram commute. Everything commutes here. Obviously, this is an isomorphism. This is an isomorphism by the theorem of these guys. And I can work out what this is, and this is brute force. This is just multiplication by minus the class of this bundle, or this module, L minus R. And that's an isomorphism. It's just a relabeling of indices, essentially. The Bott isomorphism is an isomorphism. So what I have is an exact sequence. I have vertical lines which are isomorphisms. And then I have that all of these things commute. Therefore, this guy is an exact sequence. So what we've done is we've taken, again, a sequence which we know is exact and mapped it onto a sequence that we would like to have. Therefore, the thing we have is exact. So what can we do with this? So what I would like to remind you of is that we had this map J lower star, so this pullback push forward map, where we knew we could go from algebraic generators, but we didn't know where we ended up, because we didn't know anything about the K-theory of the length space. But now we do, because we now know that we have an exact sequence. We know the K-theory of the projective space. This is what Francesca and Giovanni worked out. Therefore, we know that this map is surjective, which is not something we didn't know before. So we know that if we take the K-theory of the projective space and we map it upstairs, and we start with algebraic generators, we're going to get something algebraic, and that map is surjective. So we know that we also have an algebraic picture at the level of the K-theory of the length space. Similarly here. And we can actually do some computations. So this was, I say we, Francesca actually did these computations, so credit there. So remember that the Euler class of the projective space, this was this chi of the canonical bundle. This gives us, so this was the theorem that we had earlier, that this gives us a basis for the K0 as a Z module. And so if I have a basis as it's a Z module, so that means I can write this map alpha, this multiplication by the Euler class, as a matrix. And then you have associated to any matrix over a principal ideal domain, or in this case, over the integers. You can always diagonalize it into this form. So you can diagonalize it so that there's, so this is an n plus 1 by n plus 1 matrix. And you find that you'll always get well, that's a reordering, you'll always find that you'll get a 0 in the last column. And then a bunch of integers such that each one divides the next one. And this is all by explicit computation. I'm ashamed to say I didn't actually know of the existence of this, despite having a degree in mathematics. I wasn't aware that this existed. But you can always do this. And then once you have a matrix, you can compute its kernel and co-kernel, which is what this exact sequence tells you, is that if you want to know this K-theory and this K-theory, then it's just given by the kernel and co-kernel. The kernel is easy. That's just a copy of the integers because I have zeros here. And then I get copies of the cyclic groups of order given by these numbers. So what? Because the graph C-star algebra people will tell you, but I already knew the K-theory because I computed all of that, right? Sure. Let me give you a couple of examples. So one part of this will be already known. So for example, when R equals 2, then the N2 lens space, which is just the real projective space, you do the computation. So it's really a case of working out determinants of minors of the matrix and so on. The problem is that as n increases, the computations get very complicated very quickly, but they're in principle doable. To my knowledge, there's no universal formula. Maybe someone can correct me on that, but as far as I know, there's not a formula which says, okay, for general n and r, this is the K-theory. I mean, you have to really do the computation, and it gets complicated very quickly. But you find that there's only one non-trivial number in this computation when r equals 2. It comes out to be 2 to the power n. Therefore, the K-theory is a copy of the integers, which is generated by the trivial module, plus this cyclic group of order 2 to the n. That is known, but what our method tells you is how to get an explicit generator, and it's the pullback of the Euler class downstairs in this case. Whereas if n equals 1, so this is the lens space 1r, then there's only one alpha to compute. It's equal to r. You have to compute it, but that's what you find. So then the K-theory is again generated by the trivial class plus the torsion part of order r. And this is generated by the pullback of the canonical bundle, and we've already seen that computation. That was Johnny's original observation. I mean, in this language, it's easy to see. I think the point here is that I guess this is why I do non-commutative geometry, is because in some sense, it gives me more insight into doing classical geometry. And this is a very easy observation that I think is not so obvious if you're doing classical cohomology or something like this, at least not to me. So again, you find a generator of this group, K0. K1 we already know, that's just a copy of the integers, so there's nothing to do there. So just to stress, this is what we think of. Okay, so the K theory, the K groups were already known due to the graph C-star algebra people. Well, that's one way of doing it. We've got these generators, and the important point is here is the third contributor, the third musketeer. So the point is, as I've said, that this computation or this result reduces all of the K-theoretic and index-theoretic stuff we want to do. It reduces it all to the algebraic level. So we have algebraic generators, and we're not missing anything by working with those. And more importantly, for our point of view, because you remember at the beginning that I was saying I wanted to do gauge theory. So all of these computations of these actions and so on, I need to be able to compute this. This is a hell of a lot easier in the algebraic setting. And not only that, but our picture is geometric in the sense that we have generators in terms of line bundles, which is different to the graph theoretic interpretation. So as I told you, in the graph theoretic situation, you take generators associated to the vertices and then relations associated to the edges and so on. And you compute the K-theory via the language of the graph. What you get, the C-star algebras you get are isomorphic. But the isomorphism is horrible, horrible, horrible. I mean, if you start with a generator on the graph theoretic side and you map it over to our geometric setting, you're already dealing with infinite sums. So it's not an algebraic isomorphism. And as a word of warning to those of you who know this gauge theoretic, the graph theoretic picture, the action that we have, so this geometric U1 action, so this, the action which reduces from the lens space to the projector space, this is not what the graph theory people call the gauge action. So this is the action, the gauge action is the thing which multiplies the graph theoretic generators by an element of U1. Our action multiplies the geometric generators by an action of U1, and these are not the same. I'm not saying that you can't do stuff in the graph theoretic version. I mean, there is a relationship. But we're doing geometric computations as opposed to the graph theorists who do different computations. So, as I said, the graph theorists will say, "Hey, we knew the K theory already." But let me just say, yeah, but the action is different to what these people use, and our picture gives you a different interpretation of the answer. Natural question: what about getting K-homology for these things? Again, K-homology for these things is known, but we would like geometric representatives. That's a direction which is quite interesting and proving quite fruitful. Those of you who will say to me, "I know all this stuff, and surely you can do it by a different way," yes, you would be right. The question that I've had lots of times, I get this every time I give this talk, is can you get it from a Pimsner-Voiculescu sequence? Yes. I'm not going to tell you about that because that's not my work. This is Francesca, Jenskar, and Giovanni Landi, who I believe their work is close to being archived, more or less. So look out for that. But yes, they do a more general construction where you can get these exact sequences via cross-product algebras and so on. Yeah, sure. This Pimson algebras. Yeah, that's what I mean. Yeah. And the big question: can we do something towards Chern-Simons theory? I hope so. But this is, I think, a very big open question. So I mentioned at the beginning that Oliver Pfanter has done something to do with this. But the point is that Chern-Simons should be a topological theory. Now, it turns out that the way he writes things down ends up depending on the metric structure, on the spectral triple you use, which is interesting but not quite satisfactory enough. So maybe you can do something via this approach. We hope so. We'll see. So that's everything I wanted to say. So thanks very much for showing up first thing in the morning.
Any questions?
Yes. So, as you well know, I guess,
Hopefully.
you can twist the action of defining a singular group to generate a lens space.
Sure.
Taking different generators of a single group. So, are you able to compute with those type of lens spaces too?
I don't think so.
So, for a three-dimensional lens space, you actually have two parameters.
Yeah.
And then downstairs you have like a q-deformed.
Yes.
Exactly. These guys can do this.
Oh.
Yeah. So that's an excellent question and a natural question. This is what the others are doing, and so I'll let you get the information from them, I think.
I do want to comment again about these principal sequences, because I think it's just a matter of citing the old papers by Axel, about the Axel in the 90s. This is just a tiny special case of computations done there, so there's not any work to be done. So you just reproved the results by similar techniques that have been done.
This is the joy of mathematics, when you don't understand something, so you go and you prove it, and then you discover that other people have done similar things. I would comment that the reason, so first of all, again, I will redirect to Giovanni and Francesca about these things, but I would say that the reason that I like this construction via this lifting to the mapping cone is because it really reproduces the classical situation of the homotopy, which is, from my point of view, illuminating to see the geometry in the C-star algebras, even though you're not, you don't have these spaces that you start with in the classical situation. You can still see a kind of homotopy argument. That's what I like about it. But yes, you're right.
Any further question?
I was intrigued by the mention of the rate equivalence bimodules. So, what are they? Between what are the bimodules? So there was a mention of these line bundles being Morita equivalents.
Yeah, Morita equivalence over the base. Yeah, exactly. So this is also, as you well know, an important, well, for me, important situation in gauge theory. I mean, self-Morita equivalences are giving you the inner fluctuations, and this is a motivation for us.
Yes.
I'm not sure about Ralph's question, but in this construction, and I was late, sorry, I won't find the place. And there is the point is that it's not computed, K theory. I mean, it's some z to some power.
Yeah.
Here we compute the generators.
Exactly.
Generators in order to apply them, if possible, for the Chern-Simons materials. The second question is that for this more general lens, it's not clear that they are graphs as such. So it's this more general lens that we construct with Francesca and the ends, they may be more general, and this seems to be the only way to compute the case.
Mm-hmm.
It's not clear.
They are graphs.
They are, but it's not clear what the graph is.
No, it is. Oh, you even need
It's
to do
not
that.
clear that they are system.
Yes.
Yeah, it is. Okay, there are some assumptions that come up.
Okay.
For the more general one, it's not clear.
Yeah.
So the discussion is shifting.
Yeah.
I suggest you will go on with your discussion during the web. And so any further questions? Okay, so if not, let's thank Simon again.